Thanks for watching, and today I would like to talk about logical connectives, which are tools that help us build more complicated statements from easier statements. Just like building a house from bricks. Now, first of all, what is a statement? Just to remind you, it's some sentence that's either true or false. For instance, this sentence 1 + 1 = 2, because it's for sure true, it's a statement. Again, statement means true or false. What about this? 2 + 2 = 5. Of course it is false, but because you say, oh, it's for sure false, it is a statement. But something that's not a statement would be something like Shakespeare. Okay, nice word, but we don't know if it's true or false. And in fact, kind of it reminds me of this Office meme. Is like, you can't just say it's a sentence, it's a statement. No, I declare Shakespeare. So, unfortunately, this is not a statement, but we'll talk about those statements here. So, from now on, P and Q are simply statements. So, building blocks. And the question is, how can we build more complicated statements from those easier ones? Well, today I will discuss 3 things. One is and, the other one is or, and lastly not. And I will leave implication for another video. So first of all, let's talk about P and Q. And by the way, there's a nice mnemonic to remember this hat. Well, if you think of the word and, well, the A without the bar looks like this hat. That's why it's looked like that. And the question is, when is P and Q true? And for this, let me give you a little analogy. So, suppose you're at the restaurant and you tell the server, I want a burger and fries. If the server just gives you a burger but no fries, would you be happy? Probably not. And it's the same thing for the and statement. Namely, in order for burger and fries to be true, in order for you to be happy, you should get both items, the burger and the fries. And in particular, for P and Q, there are a lot of possibilities, right? It depends. If you get the burger and you don't get the fries, it happens that you don't get the burger, you get the fries, or maybe you don't even get any of them. Well, because there's so many possibilities, it would be nice if we could somehow draw out all of them. And it turns out there is such a thing, and that's called a truth table. And it's easier drawn than explained. Namely, what you do, you put P and Q on the left-hand side, and then the result on the right-hand side. On the left, you put all the possibilities. Say, for example, burger and fries, burger and not fries, not burger and fries, and worst case scenario, not burger, not fries. And I'm hungry. But anyway, now then you have to look what the outcomes are. For instance, if P is true and Q is true, if you get the burger and the fries, then you're happy. If you get the burger and not the fries, you're sad, so it's false. If you don't get the burger, but you get the fries, you're sad. And if you don't get anything, you're probably very mad. So press F for very mad. Okay, and again, maybe just as an illustration, I forgot to say, for instance, 1 + 1 = 2, and 2 + 2 = 5. Well, this is true, and this is false. So this is equivalent to saying it's false. And notice this is a compound statement. We have simpler statements P and Q here, and we're using it to build up more complicated statements. Now, you may say, why do we even care about this? Well, it's useful in my opinion because those logical connectives like and, they help you find the skeleton of a statement. Let me illustrate. For instance, if you take analysis, good luck, okay, you see very convoluted statements like this. Show X is compact and connected. Now, if you don't know what those terms mean, good, because this will make a bit more sense for you. Suppose you on the exam, the professor asks you, show X is compact and connected. What would you have to show? Well, it's the word and that indicates the first step. Usually if you see an and statement, what this means is you have to show two things. X is compact and X is connected. And then it's up to you to show those two little statements, okay? And I think this is great, for example, if you have test anxiety, because usually if you see all those words together, you start freaking out, like me, but if you really see the word and, it should again give you a guide of figuring out what to do. So again, here you have to show X is compact and you have to show X is connected. And this is one of the main points of this video, is first of all drawing pretty tables, but also showing you why we care about those connectives. Okay, now from the producer of and comes another sequel called or. And again, I have a nice analogy for that too. What does it mean for P or Q to be true? And again, the way you write or is simply like that. P or Q kind of looks like a nose of a beak of a bird. And here's an analogy. Well, I mean, here's the mnemonic. Well, and gives you this, or you just flip it. And think of like maybe cup looks like a U, or simply put that frown upside down. I guess here it's sad, now it's like angry. Okay, speaking of angry customers, suppose you're at the restaurant and you tell the server, I want a Coca-Cola or a Sprite. Okay, Coca-Cola or a Sprite. Now, if the server gives you a Coca-Cola but not a Sprite, then you're happy. You got what you want. If the server gives you not a Coca-Cola but Sprite, then you're also happy. If the server tells you, well, how about both, and it's free of charge, then you're still very happy. And in fact, this is the point of view that we'll take in this video or in math. An or here is an inclusive or. We accept both to be true. So if P is true and Q is true, then the or statement is true as well. So, which again gives us a hint at the truth table. Again, true, 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 false, false, true, false, false. Well, if you get a Coca-Cola and a Sprite, then you're happy, because it's an inclusive or. If you get a Coke but no Sprite, you're still happy, you know, because you got your beverage. If you get no Coke but a Sprite, you're still happy, you get your Sprite. But if you don't get anything, then you're mad, okay? Because you don't have your beverage, and therefore we have F here. And again, just to illustrate, 1 + 1 = 2, or in fact anything else. The question is this true? Well, yes, because this statement is true. So you see, you didn't even have to look at the other statement anyway. And why is this useful in math? In my opinion, for something called proof by cases. So you might have statements like, suppose n is even or odd. So kind of an or statement, you know, I can't even. Then, because you see an or, it usually indicates to do it by cases. So usually the way you do this, you say, well, first suppose n is even, and then you do your proof. or you say suppose n is odd, and then you do your proof like that. So again, or is a good indicator of cases. Last but not least, something quite fun. Oh no, never mind. We'll do it at the end. I forgot, because we need to introduce the term not, which is Borat's favorite connective, not, okay? And that was interesting because before we had P or Q, P and Q, stuff that depends on two things, and what's called a binary connective. Now we just have not P, which is an unary connective. So it just depends on one thing. P and not P. And not P is called the negation. It says the opposite of whatever P says. So if P is true, not P is false. If P is false, not P is true. Now, why is that useful? Sometimes it's easier to prove or disprove the negation than the statement as itself. For instance, so consider the following very complicated statement. For every, let's say even integer, there exists another integer y. So for every integer x, there exists an integer y such that x equals y squared. You might guess what the answer is, but in my opinion, this is already complicated. So instead, let's try to prove or disprove the negation. So the negation of this, you simply turn n for all into there exists. So does there exist an integer such that no matter which other integer we have, you cannot write it as a square? In other words, what this is saying is there an integer that's not a perfect square? And in fact, this is true because you let x equals 2, and it is true that 2 is not of the form y squared for any integer y. So because not P is true, it actually implies that P is false. So in fact, the original statement itself, without the not, is false. And you see, this is why sometimes it's easier to prove the negation than the statement itself, and it's also kind of almost the basis of stuff like proof by contradiction and maybe proof by contraposition. Last but not least, the fun thing I tried to do at the beginning is the following. What can you tell me about P or not P? Well, look, if P is true, this is true. If P is false, then this is true, so this is true. So this thing is always true. Well, here's the fun thing. Let P be to be. Then what this becomes, to be or not to be. So when Hamlet asked to be or not to be, that is the question, well, the mathematicians would say to. That is the answer. And I'll end with that because I'll do P implies Q in a different video because it's a case apart. So if you like this and you want to see more math, please make sure to subscribe to my channel. Thank you very much.